from the homework. 1, 5, 2, 1, or 2, 2? I only see 2 faces. Feel free to turn on your cameras.
I guess I have one question about like completing the square. Like I understand the first part where you, I guess, take the C value and put it to the other side, but I don't know, it just gets all jumbled up and I don't understand how to do it.
Do you have an example of a completing the square problem you want to go over? If you do,
I just had a really hard time on the homework with square.
And if anyone else has a completing the square problem you want to go over, feel free to pop in and it might be helpful. Are you looking for one, Mia? Oh, you're muted.
I'm looking through my notes and stuff.
Okay.
I think I tried to solve 1 or 2. Gotta find my notebook.
No problem. Other than the quadratic stuff, so it seems like the function stuff from 2, 1 and 2, 2 went better.
I have a question on the homework.
Okay.
Like on Pearson.
Yes.
I didn't get to finish all the homework, but I wanted to know if I noticed that you could still like review it. Can you like can you still like put in the answer? I'm not sure how Pearson works, but could you still put in the answers and it'll tell you like if it's wrong or right?
I think when you're reviewing it, yes, you can still work on it. I'm pretty sure. I'll have to verify that, but I'm pretty sure that like even if you like didn't do an assignment, you would still be able to go through the assignment later on and work on it. I'm gonna verify that though.
Okay. I emailed you so because I just noticed I asked you if I could still review it, but I just noticed that you can. I just have to try and type in like to see what I get. If it tells me if my answer was right or wrong.
You're saying you're not sure if it will or it's not doing it?
I'm not sure if it will because right before class I was doing a problem, but it told me like my equation wasn't right or something, like the format. So I'm not sure if I try something else, it will tell me if it's correct or not. So I'll try it as well later and I'll let you know.
Okay, yes, let me know. Because yeah, that would be really helpful to know.
Okay.
Okay. Mia, did you find one you wanted to go over?
Yes, 2x squared plus 5x minus 3. And then completing the square for that.
Equals 0?
Yeah, equals 0.
Okay. All right. So this is a good one for completing the square. Do you happen to know which number this was on your My Math Lab homework or no?
No, not really.
Okay.
Might have been the first ones.
Okay.
Yeah.
It is sometimes helpful when you're doing the homework if you write down the 3-digit code. So like, for instance, this was section 1.5. So it should say like 1.5 point something, just so I have a reference point. So let's say you did that problem on your homework, but maybe you wanted to see another one like it, then I could pull it out of the book. You don't have to, because even if you have, you know, the problem you want to go over, that's fine too. But then at least somebody else can look it up and say, oh yeah, I had one similar to that too, and that answers my question.
Mm.
Okay, so this one was solving by completing the square, you said?
Mm-hmm.
Okay, so the first thing we do when we're completing the square is we want to bring the constant to the other side of the equation. The second thing we want to do is make sure that the coefficient of x squared is 1. So we're going to divide each term by the coefficient of x squared.
Mm.
And I'm guessing we were all probably fine up to this point. Does anybody have a question here? Okay. Wonderful. All right, so now we're gonna start the process of completing the square. So I'm gonna take the middle term's coefficient, which is 5/2. We're gonna take half of the middle term's coefficient, and then we're gonna square it. And that's the quantity we're gonna add to both sides. So when I take half of this quantity, I get 5/4. And then I'm gonna take 5/4 and square it to get to 25/16. And this is what we're gonna add to both sides. So back to this row, we'll take x squared plus 5/2 x plus 25/16 equals, and then on the right-hand side, we'll have 3/2 plus 25/16. So everything stayed the same. It's just that on each side, we added a quantity. Now, looking at this really looks like one I did in the office hour with Jasmine. It might be the same problem with different numbers. We'll see. Questions so far?
I have a question.
Yes, Karen.
When you multiply the 1/2, was that to get rid of the, that's to get rid of the exponent, correct?
Right here?
Yeah.
I just multiplied by a half instead of dividing by 2 because we always take half of the middle term's coefficient and then we square it. So I just took half by multiplying it by a half.
Okay.
Other questions? Okay. All right, so the whole point of completing the square is we want to get a perfect square trinomial on the left-hand side so we can factor it, and then we'll have a binomial squared. Once we have that, we can use the square root property to take the square root on both sides of the equation, like we did at the beginning of 1.5. So to factor the left-hand side, you're going to use the variable to the first power, keep the sign that's in front of your middle term, and then you're going to take half of the middle term's coefficient before you squared it. So half of 5/2 you got as 5/4. That's what goes inside your factored form, and then you square the quantity. I think that's probably a step that people are getting stuck on right there, is that whole process of factoring. On the right-hand side, we're going to simplify. You can put this into your calculators if you prefer. You can get a common denominator, in this case, of 16. 2 times 8 is 16. 3 times 8 is 24. So 24 and 25 are 49. And then your denominator is 16. Yeah, this, I think, is the exact same problem I did with Jasmine with different numbers. So it sounds like more than one person struggled with it. So I'm really glad we're doing it. Now we're going to simplify it. So now we have this in the form such that the left-hand side is a quantity squared and the right-hand side is a constant. We're going to use the square root property to solve the equation. Let's go ahead and take the square root on both sides. Remember that when you take the square root on the right-hand side, you have to apply that plus or minus. Now, I'm going to show this with the square root symbols. You don't have to do that in this case because 49 and 16 are both perfect squares. So if you want to go right to saying 7/4, that is fine. You don't have to include this step. I just want to make sure that I include it in case there are questions about it. And now once you're here, you're almost done. So we have plus or minus. We'll take the square root of 49 and the square root of 16. And then we have x equals negative 5/4 plus or minus 7/4. Now you can't leave your answer like this. You do need to simplify both of those answers. One of them is negative 5/4 plus 7/4, and the other one is negative 5/4 minus 7/4. Negative 5 plus 7 is 2, and 2/4 is 1/2. Negative 5 minus 7 is negative 12, and negative 12/4 is negative 3. Now, somebody had asked me this weekend, I think it was Angel. There was a question that had like a lot of simplifying with radicals. Did anyone have another one of these that they wanted to go over, or are we feeling better about this? Okay. Anything else from the homework?
I was confused. I was just gonna I have to like rewatch the video because I was confused on this lesson. When you, I know you said that you divide at the top, you divide by 2 or you multiply by 1/2. Why do you then why do you multiply like that by 2, like the exponent 2?
You mean, why do we do this? Well, we always do two things in order to make this a perfect square trinomial. The definition of a perfect square trinomial is that the constant in the trinomial is half of the square of the middle term's coefficient. So if we're trying to create a perfect square trinomial, we have to set it up so that our constant is half of this term squared. So those are the two things we always do to that value. Does that answer your question, Karen?
Well, usually when we do any step, we're undoing or like the 1/2 you did to divide. But where do you get the 2 from? Is there any other reason?
You mean this one?
Yeah.
That's just because we're trying to force it to be a perfect square trinomial. If I can go back to our 1.5 notes, let me pull that up here, because I had up here the definition of a perfect square trinomial.
Does that 25/16 replace anything in the equation, or it's just there extra for that perfect square?
We're just adding it in so that we can create a perfect square trinomial on the left. And then because we're adding it to one side, we have to add it to both.
Okay.
So it's not replacing anything. We're just trying to create something that wasn't originally there.
Okay.
Let's see. I thought that I wrote this out much more nicely. Oh, you know what? I did. It's in this packet of papers. So, Karen, what I'm referring to is from section 1.5 on the notes. Let me pull it up here. This formula at the top for creating that perfect square trinomial.
Oh.
We can factor in this form as long as we have this form on the left. So to create this form, we have to take b, then we take half of it and square it.
Okay.
Does that help?
Yeah.
Okay. I know it's weird because it's not the most intuitive thing to do, but that is the process. All right. Anything else from last week or the week before? Let's go ahead then and finish these notes from 2.2. Oh, by the way, I totally forgot to send an email. I clearly was really enjoying my Labor Day weekend. So 2 people emailed me to let me know that they received their class notes for 2.6 through chapter 8. So if you did not receive your class notes for the rest of the semester, keep an eye out. I think the first person emailed me Friday. I think it might have even been Friday. So you should have gotten them now. Okay, Sebastian says he got his too. So if you did not get your class notes, it could be that you were not on the roster at the time they were printed, or maybe, I know someone had mentioned that they moved recently and maybe their address wasn't updated. Double check that, because we're gonna have to figure out a way to get notes to you. I don't think the copy center is gonna let me do another round of printing. I don't know. I'll have to bother them again. Okay, good. So it sounds like people are getting them. Good. Wonderful. Benjamin, if you need to update your address, I think you do it in Access ECC, but I'm not positive. You might have to call and ask how to do that, but I think you can do it through Access ECC. All right, let's see here. What am I doing? There's my meet. Here's my sheet of notes. All right, let's finish up 2.2 here. It's kind of a long section on functions. I don't need to finish all of this. Some of it's kind of fluff that's just extra. But we do need to talk about piecewise functions. Students don't like piecewise functions, and I don't know why. Even in calc, students are just like, what? What is this? What am I supposed to do with this? That's why it's really important that you learn how to work with piecewise functions in college algebra so that when you see them later on down the road, you're not completely confused about what a piecewise function is and whether or not you've seen it before in your life. We are going to be graphing piecewise functions and evaluating them. Also, this will bring along your first homework assignment that I'm going to need you to complete by hand. And I'm going to be sending you some email instructions for that. But I'm going to be assigning 3 questions from 2.2 where I want you to graph these. And oh, it's actually 4 from 2.2 where I'm going to want you to graph them and turn them in by hand. So I will send you guys an email later on tonight so that you'll know which ones I want you to do, and just make sure you understand the process. And as soon as you do them, you can submit them. You don't have to wait until next week. But I want to see you graph these by hand because it's a much different skill than doing these on my math lab. On my math lab, it's multiple choice. On an exam, I'm going to have you do it by hand. So having you do a multiple choice on my math lab isn't really going to teach you much about piecewise functions. Evaluating them is a different story, but graphing them, I'm going to need you to do by hand. So I will send out those instructions tonight so you have them. I know some of you get started on your homework right away. Others wait. Everyone's got a different schedule. A function that's defined by 2 or more equations over a specified domain is called a piecewise function. It's just a function that you're graphing in pieces. And when you see the function defined, it'll say f of x equals, and then you're going to see a brace. And then it's going to have at least 2 different functions with a range of values for which that function is to be graphed. You could even see piecewise functions down the road that have, 5 or 6 different functions in them. In this class, we're just going to be looking at some basic ones. I just want you to know what they are. I want you to know how to graph some simple ones. I'm not going to ask you to do anything super crazy. What this function means is that for any value of x that's less than 2, that means less than 2 does not include 2. So like 1.9, 1.99999 are fine, but as soon as you get to 2, it's not included. You're going to follow the rule f of x equals negative x plus 3. For any value of x that's greater than or equal to 2, you're going to follow the rule 2x minus 3. Now, there are different schools of thought for how to do this, and it kind of depends on what you've been doing in algebra most recently. We haven't really been talking about slope-intercept form or graphing using the slope. If you remember how to do that, you're more than welcome to just start graphing these using the slope and the y-intercept. We have been talking about graphing by plotting points. So that's how I'm going to show you to do this. I'm going to start just by looking at the first function, which for us is f of x equals negative x plus 3. And then I'm going to make a separate table of values for the second function, which is f of x equals 2x minus 3. Now, for the first function, I'm not just going to say that I want to use any 5 values at random. I know that this function only corresponds to values of x that are less than 2. So you could use the values that we've been using a lot of, like -2, -1, 0, 1, but don't use 2. We'll talk about what to do when we approach that value, but for now, just look at some integer values such that x is less than 2. And for the second function, that corresponds to values that are 2 or greater. So maybe 2, 3, 4, 5, something like that. And then we're just going to figure out what these function values are, and we're going to plot some ordered pairs that correspond to these points. So for negative x plus 3, well, if x is negative 2, we'll take negative 2 plus 3. Negative of negative 2 is 2, plus 3 is 5. So that will give you an ordered pair at negative 2, 5. And if you want, you can plot that now. Might as well, since I just mentioned it. So x is negative 2, y is 5. That point is right here. For x is negative 1, we have negative x, so negative 1 plus 3 is 1 plus 3, which is 4. And that puts us here at negative 1, 4. Now, this is a linear equation. If you can see what's happening at this point, feel free to just follow that slope and move along. All right. When x is 0, f of x is 3. And then when x is 1, we'll have negative 1 plus 3, which is 2. So if you were to get some value that was way off up here or down there, you would know something is wrong because this is a linear equation. You're expecting it to be a straight line. If you'd like, you can connect those. If you want to wait, I would probably wait just because we want to talk about the behavior that's actually at that boundary of 2. Before I proceed, does anyone have a question? Okay. All right, so let's go ahead and fill in some values for the second function. We're taking 2 times x and subtracting 3. So we'll go ahead and just fill out the table. We have 6 minus 3 is 3. 2 times 4 minus 3 is 5. And again, this is linear, so you're going to see a pattern here such that the difference between these values doesn't change. All right, so we have a point at 2, 1. We have a point at 3, 3. 4, 5. And then the one at 5, 7 is, well, I guess we can graph it right up there. So at a first glance, this looks just like a V-shaped graph. Clearly, it's not an absolute value because you have different slopes on each side. Let's go ahead and start to connect these lines. Notice that for any value of x greater than 2, we're following this line. So you can go ahead and connect these, show the arrow notation heading upward and to the right. If you'd like to use a straight edge, that's fine. But be very careful when determining what's happening at this boundary value. Think about, for instance, what if we had talked about what value f of x is approaching if we let x be 2. Now we know that the value of 2 is not defined for this function, but if we had used that value, we would have gotten a point at 2, 1. Now, this could go either way. In our instance, the point at 2, 1 is already on the graph. You know that your line would be approaching that point at 2, 1. If we didn't already have a point at 2, 1 from the other part of the function, we would leave an open circle there. But because the other function is already defined at this point, all we need to do is connect these. And again, you're sending that arrow off up and to the left. We are not going to put arrows heading down and to the right here or down and to the left for the second function because the last value on this line is the value that happens when we approach 2. And the first value on this line is the one that happens at x equals 2. This is the piecewise defined function. If you'd like to draw a dotted boundary line, you can. You don't have to. Some students like to include it just so you can see where those values change. But this one is, I think, a little bit more obvious, not too crazy to see. And that's how you graph a piecewise function. Does anyone have a question on the graph? Okay, and like I said, you'll see those in calc. Sometimes you'll see half the function will be quadratic. It might look like a parabola, and the other half could be a linear equation. In this class, I'm not going to give you anything super crazy. It's probably just going to be straight lines. I just want to make sure you can graph them. Now, once you have the graph, you can evaluate the function. Now, it's up to you if you want to use just the graph to evaluate the function, or if you want to go back to the definition. I'd probably go back to the definition just in case I accidentally graph something wrong. I don't want to be depending on wrong work in order to evaluate the function. So when you're evaluating this, you're being asked to find different function values. One of those values is f of 2. Well, in order to figure that out, you need to figure out which function corresponds to a value of x equals 2. And the value that corresponds to x equals 2 is the second definition, f of x equals 2x minus 3. Remember, the first definition only works for values of x that are less than 2. So we can go ahead and evaluate this function at 2, and it should match the value that you have on your graph, because really you already evaluated it at 2 up here. So you'll have 2 times 2 minus 3 is 1. And this is also kind of just going to serve as a check for the work you already did. If you end up getting 2 different answers, you'll know, whoops, something is wrong. Better go back and check. So when x is 2, f of x is 1. For f of 0, 0 falls under values of x that are less than 2. So for f of 0, you're going to use the first function. And you'll find f of 0, which again, you already have up here in your table. When x is 0, f of x is 3. Now, f of 10 is not one that we graphed. You're not going to see it in your graph. It's not in anything in your table. You just need to figure out which part of the function this will apply to. And that's any value of x that's greater than or equal to 2. So you're going to, again, use 2x minus 3. And then we'll just substitute in 10 for x. And you'll get 17. Questions on the piecewise function? I think this will serve as a really good tool as you go through these problems on your homework. But if you have questions, because it won't be on my math lab when you're doing the graphing part, feel free to email me. If you want, even just send me a picture of your work and say, is this graph correct? I think it is, but I'm not sure. It looks funny to me. If you're not sure, just send it to me. The questions I will ask you on my math lab will look more like this. You'll be given a piecewise function and you'll be asked to evaluate. But the graphing I want you to do by hand. When we're evaluating at the bottom, will they always be in your tables? No, they may or may not be. It may be a value that you randomly chose, but it might be a value you didn't cover. So it might just be one where, like 10, you'll have to actually just evaluate it from scratch. Anybody else questions about the piecewise function? Okay. You know, number 10, I'm going to skip just because it's kind of a common sense problem, and I didn't really see how we were going to use it that much mathematically here. So I said skip it. And we'll talk about this difference quotient. The difference quotient is another thing that you're going to use a lot if you take calculus. Sorry for those of you who are not taking calculus. This is definitely geared towards getting you ready for computing derivatives. So it's very helpful for that. So the difference function looks like this. F of x plus h minus f of x divided by h. So when you're being asked to find the difference quotient, that's what you're being asked to find. And a lot of times your answers here could have h's in them. That's okay. Sometimes they'll cancel out. That's okay too. I'm going to give you 2 examples here so you get used to using this process and kind of seeing what's normal for your answer to look like. Yeah, then you'll have a couple of these to do in your homework. So for a difference quotient, and if, like I said, if you're looking for like a real world grocery store application here, I don't have one. This is just because you're going to be expected to do it in calc. Find and simplify the difference quotient. Our function is f of x equals 3x minus 7. So we need a couple of things here. One of the things we need is f of x plus h. So I'm going to find the individual components, and then I'm going to put the whole thing back together again. So we have f of x. We need f of x plus h. So we're going to evaluate this function at x plus h. To do that, we're going to take the x and replace it with x plus h. And make sure that you're using parentheses here because x plus h has to have this 3 distributed in. That is your variable. And then to simplify this, we'll just distribute the 3. You'll have 3x plus 3h minus 7. All right, so our formula needs f of x plus h, which we just found. Then we're going to subtract off f of x, which we were given, and divide by h. So let's piece this together into the difference quotient. We're going to take f of x plus h. I'm going to label this so that you all can see what the parts are. So there's our f of x plus h. We're going to subtract off f of x. Now, it's very important that we put parentheses around our expression f of x because it has 2 terms in it. And you're subtracting off both terms. If you don't include the parentheses, this minus 7 won't get flipped into a plus 7. We're subtracting off the whole thing. It needs to be offset in parentheses. And in the denominator, we have h. Some of you will find this to be very fun. It's true. Questions here? Okay. All right, so let's simplify. 3x plus 3h minus 7. Now we're going to distribute this negative sign into the parentheses for f of x. So we're going to have minus 3x, and then minus negative 7 is plus 7. And then we'll simplify. To simplify, we're going to combine like terms. You have 3x minus 3x. So the 3x's are going to cancel each other out. And then you have a minus 7 plus 7. Those are additive inverses. They cancel each other out. So what you have left here is just 3h in the numerator divided by h in the denominator. And h is a common factor in the numerator and the denominator. H over h is 1. That means your difference quotient simplifies to 3. So these linear ones are going to be super straightforward. Questions on number 11? Okay. So when your function's linear, meaning the degree of your expression is 1, you just have x to the first power, no variables in the denominator, you should end up getting this to simplify down to a constant. That will not be the case for something like number 12, which is quadratic. It's quadratic because it has degree 2. But we're going to do this the same way. We're going to start out by finding f of x plus h. Then we're going to put everything together in the quotient. We're going to remove the parentheses and do our subtraction and simplify. The main difference here is that when we're finding f of x plus h, you must remember that you have 2 different terms that have x in them. So you cannot just apply x plus h to this term. You have to also remember to evaluate this term at x plus h. So we're going to take x plus h squared plus 8 times x plus h plus 1. Does anyone have a question here? Viviana, do you have a question? It's so helpful that your camera's on because you look confused. Do you have a question or no? Okay. All right. See, it's if you guys turn your cameras on and I see that you look confused, then I'll know. You don't even have to bother asking. Right. All right, let's start to simplify this because right now this in and of itself is something that needs to be simplified. Remember that when you take x plus h and you square it, it's a binomial, you have to FOIL it out. This is not x squared plus h squared. It is x plus h times itself. And then we can, if you want, go ahead and distribute that 8 into the parentheses. 8x plus 8h plus 1. Now we're going to do the FOILing, and then we'll combine any like terms if we have them. So you have x squared. Now, when you FOIL, you're going to have x times h and x times h. You're going to have 2 of those terms. So we're going to say 2 xh. Now, if you want to call it hx, that's fine too. You can combine those in either order. If you find this weird, I'll do it in 2 steps. So you have xh plus hx, same thing, plus h squared plus 8x plus 8h plus 1. This is one of those things where I don't want you to look at your notes while you're doing your homework and wonder, how did she get that? It should be clear from your notes. I want to make sure to include all the steps. All right, so we have an x squared, xh, and hx. It's multiplication. You can commute those in either order. So we're going to just call them both xh, and we have 2 of them. And unfortunately, that's as simple as f of x plus h is going to get. Now we still need to find your difference quotient. Before I do that, does anyone have a question on f of x plus h? Okay. Wonderful. So now we're going to take f of x plus h minus f of x, and we're going to divide that whole quantity by h. So I'm going to rewrite the f of x plus h. It's x squared plus 2hx plus h squared plus 8x plus 8h plus 1 minus, and here's where we're going to take off f of x. And I can label this again if you find that helpful. I want to also take this opportunity to remind you that you cannot cancel out h's here and here or there and there. Remember that in order to cancel them out, you have to have them in every single term, which we don't have here. So if we get to a point where we can cancel them out, and we will in a minute, you have to make sure that you have the right circumstances. Let's go ahead and distribute that negative sign and simplify the numerator. X squared plus 2hx plus h squared plus 8x plus 8h plus 1 minus x squared minus 8x minus 1. Divided by h. So everything stayed the same. The only difference is this minus sign was distributed into the last three terms when we subtracted off f of x. And again, don't be canceling. You cannot cancel out anything with this h at this point. What you're going to see happen in all of the cases with these quadratic functions is you're going to end up getting these last three terms to be additive inverses with terms you already have. Like, for instance, you have a minus 1, you have a plus 1. You have a minus x squared, you have a plus x squared. And you have a plus 8x and a minus 8x. So all three of these terms in your minus f of x are going to cancel. And what that's going to leave you with is 2hx plus h squared plus 8h. I think that's it. Let's see, 2hx plus h squared plus 8h. Yes, because this term went, that term went, and this term went. Divided by h. It starts to simplify very quickly. Elizabeth, do you have a question?
Does this mean that we can cancel out the h's because they're in every term?
Yes. At this point, because you have an h in every single term, you can cancel out one factor of h. If you don't feel comfortable doing that, show it so that it's factored out. You can factor the h out, and that leaves you with 2x plus h plus 8. And now it's a little bit easier to see that you have a factor of h in the numerator and a factor of h in the denominator. Now, you don't have to do that. If you feel comfortable just saying, I can get rid of one in each and every term, that's fine. But this is your simplified difference quotient. So remember that in order to cancel out a common factor, that factor must be common in every single term in the numerator and denominator. As long as that's the case, factor out as many factors of that variable as you can. You only had one here, and one there, so that's all you can factor out. Or cancel out, I should say. So that's the difference quotient. Questions there? Okay. Okay, number 13 is about the greatest integer function. I pretty much never do that. It's something that you're really not ever going to use, hardly ever. If you ever see it again, it's going to be like 6 years from now when you're in grad school. Yeah, I'm not too worried about it. I always forget what the definition of the greatest integer function is because I have used it so few times in my life. So we'll skip number 13. No big deal. If you're really interested in it, it's in your book on page 236. All right. That is 2-2. I had mentioned last time that 2-4 is review from your algebra days. It's an optional section. We're going to skip it. And we'll move on to 2-5, transformations of functions. This is the last set of notes that you should not yet have. So starting with 2.6, you should have been mailed those notes and you won't have to worry about it anymore. 2.5 is the last one that you have not been sent. Okay, so we did some examples last week. I believe it was in 2.1, where we graphed two functions, and then we asked about these two functions, how are they similar? What changed between the two functions? I'm going to go back and show you those because it's what we're going to be doing today. It was in 2.1. We graphed functions by plotting points. We graphed -2x and -2x minus 3. And then some of you volunteered that the functions were similar because you could tell that they were parallel. And that's true. What we're going to talk about today is the fact that these functions are basically the same, except the function g of x had a number being subtracted from it. So we're going to talk about what happens to your graph when your function definition has a number added to it or a number subtracted from it. Or what happens if we were to multiply x by a number? Or what would happen if we took a negative value of the function? How would that change the graph? So that's what we're going to be focusing on today. And 8 was the same way. You had the absolute value of x, then you added 2 to it. And the first conclusion we're going to come to in 2.5 is this whole property of a vertical shift. So let's get into that now, because it is your easiest transformation. On your calculator, graph the following 3 functions below on the same set of axes. Make sure to label each graph with its function equation. Whether you do this in your calculator does not matter to me. I'm going to remind you of how to do this just in case you find that useful to check your homework. But let's go ahead. We'll graph them in the calculator this time, and then we'll jot them down and talk about how our functions are similar and how they're different. The first one is f of x equals x squared. Oh, sorry, this is at a weird angle. Or maybe I just need to make it darker. I don't know. I had this problem last year, and I thought I just made it darker. Yeah, maybe not. Oh, no. No. Well, I'll do my best. You know, if my calculator wasn't so fancy, I wouldn't have this problem. I wish my children hadn't completely mauled my 83. All right, x squared. You're going to enter an x. And if you have this squared button on your calculator, that's fine. It's this button right here. If you don't have the squared button, then you'll hit the caret. Your calculator, if it's older, will probably give you a caret. Mine just raises an exponent. Goodness. You know, you guys can't see this at all, can you? I'm gonna have to get that emulator. Okay, I will ask her for an emulator. Don't worry. They asked if we needed it, and I didn't think I did, but clearly I do. All right, so when you're graphing x squared, you get this quadratic function. If you already were messing with your window from last time, it'll be all screwed up. So you'll go to the zoom button and you'll hit 6 for zoom standard. You could try turn. Yeah, I did try turning the brightness down, but this is as low as I could get it to go. I guess this is as dim as it goes. So you can kind of see it if I turn it to an angle. Yeah. Yes, Stephanie, you're right. But I tried it and I can't get it to go any dimmer. Such is life. All right. If you need help graphing anything on the graphing calculator, shoot me an email. This is a function that is from your library of functions that we should be able to graph by hand anyway, your standard quadratic function. The points on it are 0, 0, 1, 1, 2, 4, 3, 9. It's x squared, so it takes every value of x and squares it to get to y. So 1 squared is 1, 2 squared is 4, 3 squared is 9. And it goes the other direction. Negative 1 squared is positive 1. Negative 2 squared is positive 4. Negative 3 squared is positive 9. In the future, I will have this emulator so I can just show you like the calculator computer version of this. Did not realize I had this working last semester so that everybody could see it. This is f of x. G of x is going to be this same graph. Here, I'll kind of put it off to the side maybe so you guys can see it a little better. Well, that doesn't even help here. X squared plus 4, same idea. So x squared plus 4. Be careful. You can kind of see this from my calculator screen. Make sure that your plus 4 is not in the exponent. Like for instance, when I open an exponent, it will just automatically keep everything. I'll show you what it does if I can. When I go x squared, if I don't send it down, it'll just type everything behind in that exponent, which you don't want. You want the plus 4 to be on its own. That happens to me all the time. So make sure you X out of there and then add 4 to it. Now what you end up getting is this graph G of x, where really all you have is your original graph of f, but it's been shifted up 4 units. Now I'm going to graph G in red. So when you see this plus 4 in the function definition, that means that it's a shift up 4 units. So for G of x, it's just going to be f of x shifted up 4 units. To graph that, you can take every point that you have on f of x and just shift it up 4 units. The easiest place to start with this would be that point you have at the origin. Just move it up 1, 2, 3, 4 units. And then this point at 1, 1, move it up 1, 2, 3, 4 units. Same thing with your point at negative 1. And you can even move your point at 2, 4 up 4 units. So you have a point at 4. Now it's going to be at 5, 6, 7, 8. And 5, 6, 7, 8. Where was I? 5, 6, 7, 8. So this will be your function G of x. Does anyone have a question about how I was able to generate G? Okay. Now for H of x, you have x squared minus 3. Now that's going to be a downward shift, as you saw from what we looked at in those notes from 2.1. But you can always verify that on your calculator by going to your y equals menu, to really turn this to the side, and entering x squared minus 3. And when you graph that, now you're going to see a third function that has a vertex below the x-axis. So that one, H of x, is a shift down 3 units. So this is f of x shifted down 3 units. So you're going to take all of the points on your function f, and you're going to shift them down 3 units. So 1, 2, 3, your new vertex is 3 units below the x-axis. 1, 2, 3. 1, 2, 3. And you should see that you still are able to retain that same shape. And there is symmetry here with your quadratic function. So once you generate those points on the right, you can use symmetry to get the points on the left. You also had a point on f of x at 3, 9. You can shift that down 1, 2, 3 units. And 1, 2, 3 units to finish off your graph of h. Now, you should have spent some time in your previous algebra class graphing quadratic functions. If this is the first time that you've seen this square function, I'd be pretty surprised, but it may have been a while since some of you have seen it. So feel free to use your calculator to generate those graphs. Again, so sorry that this is not coming up properly, but you can, I hope, see. I mean, the graphs come out okay. It's just hard to see my functions. But that is how you would enter this on your calculator, which of course you'll be allowed to use on your exams. The main goal here is to graph some examples and then to just make a general rule about what is occurring here whenever we add or subtract a value from the function. So keep in mind here that in each one of these functions, you had x squared as the first term in the function. But for f of x, you were adding nothing to it and subtracting nothing. For g, we were adding a constant, and for h, we were subtracting a constant. Now, it makes a big difference that this is a constant. We didn't subtract 3x, we just subtracted 3. Big difference. Because we subtracted and added a value and we found that we were able to get this graph to shift up and down, we're able to now make this conclusion about a function f of x plus or minus k. So in general, for any function f of x, how will the graphs of f of x plus k and f of x minus k relate to the original? Well, we can go ahead and make the conclusion that f of x plus k will shift f of x up k units. So you have a function, you're adding a constant to it, the function's going to shift up that many units. F of x minus k, this is going to shift f of x down k units. So some really important conclusions here. Does anyone have a question about number 1? The nice thing about this is that you can indeed verify these points. If you didn't believe me and you wanted to graph this by plotting points, you could plug in some numbers and verify that that's what's really happening in this graph. But you know, it makes sense. You're taking all the values of the graph and adding a number to them or subtracting a number from them. All right, the next thing we're gonna do is look at our absolute value function. I am going to show you how to graph this in your calculator. I bet you if this room was brighter, it would change the contrast on my calculator. Oh well, not much I can do about that. To graph an absolute value function, that's our f of x here, the absolute value of x. If you're not sure how to pull that up, you can hit the math menu, which is this button right here on your calculator. And it's going to pull up a menu of math topics. Scroll to the right to the number column. And the first option is ABS for absolute value. And hit enter. Now on my calculator, it's a little bit newer. It's going to give me a template with absolute value bars. Yours might just say ABS parenthesis. If that's the case, just enter an X in the parentheses. I'm going to enter an X in my template. When I graph the absolute value of x, I should get a V-shaped graph. We know this because we've already graphed absolute value functions. We know what they look like. Any questions on how to generate the absolute value graph? Yes. So can I go over this again? Absolutely. So when you're trying to graph an absolute value function, sorry, Sebastian, I hope you can at least see this enough to get a good idea. I feel so bad. I know, I feel so primitive right now. All right, we're gonna hit the math button. You're gonna scroll to the right to get to the number column. And the first option is ABS, which is absolute value. And you can just hit enter, or you can hit 1. If your calculator just says ABS parenthesis, put an X in it. Mine happens to pull up a template, so I'm just gonna enter my variable X in the template. And I have the absolute value of X. There's gotta be a better way. In my bars. And then hit the graph button, and it'll pop up that V-shaped graph. Okay. Did that help, Sebastian? Yes. Okay. Any other questions on how to graph the absolute value graph in your calculator? Okay. Wonderful. All right, so we have the absolute value of X. This is your standard absolute value function. If you're not sure what the points are on it, by the way, this is like the worst day for me to have this problem. You can go to your table, which we looked at the other day. I'm going to remind you, you hit the second button and then the graph button, and it brings you to your table. Yikes. Second table. You can kind of see the values in here, but this will just give you ordered pairs. So it says when X is -3, Y is +3. When X is -2, Y is +2. When X is -1, Y is +1. But this is where those V-shaped numbers are coming from. You can always refer to your table. Yours will look much nicer. It's very hard to see mine. All right, so let's go ahead and graph our function f. Remember, we just let x be whatever number we want. F of x is just going to be the positive value of that number. The absolute value of 1 is 1. The absolute value of 2 is 2, so on and so forth, which is where this V shape is coming from. The difference is that when we're to the left of the y-axis, when we're looking at values of x that are negative, f of x will be positive. When x is -1, well, the absolute value of -1 is +1. And that's where you get this V shape. Go ahead and connect those with a nice straight line. And you'll probably want to label it F because you want to make sure that you can compare it to the transformations that are going to occur. Any questions about how to graph F? For G, same idea. I'm going to go into my y equals. I am going to go to y sub 2. I'm going to hit the math button. But G is the absolute value of x plus 2. I'm going to scroll to the right to the number column to get the absolute value. Then I'm going to hit enter. And then inside the absolute value bars, I want to have x plus 2. It's very important in this case that the +2 is inside the bars. Now, from what you saw in example 1, if the +2 was outside of the bars, then that would be a shift up 2 units. However, right now you've got the +2 inside the absolute value bars. And watch what happens to your graph for y sub 2. Interesting. This is not a shift up 2 units. It's actually a shift 2 units to the left. So your vertex for the original graph was here at the origin. For your new graph, it's shifting to the left 2 units. So we're going to go ahead, write that down, and then graph our function g. So g of x is going to be f of x shifted left 2 units. Now, this is the one that always throws students off because anytime you see a plus sign, you think up or you think right. But when it's a horizontal shift that moves to the left or right, the plus sign inside the absolute value bars actually means you're going left. And some of you are thinking, then it must be the case that if it's a minus sign, it moves to the right. And you'd be correct to think that. So the plus sign means that we're going to the left that many units. So to make our graph G, we're going to shift all of the points for F 2 units to the left. If you want, you can just use that same, up 1 over 1 slope for your graph and just shift the vertex left 2 units and kind of go from there. You don't have to actually visually move every single point left if you don't want to. You can just use the slope. I mean, you can see now that you're going to have the same behavior. So there's our G. And all of those functions move 2 units, or I'm sorry, all of those points move 2 units to the left. I know this section can be kind of tedious, but I think it's such a great section because I think it's really important that we can look at the definition of a function and have a good idea right off the bat what the graph is going to do. So we know something about, absolute value functions and what they do, but we don't want to wonder like, oh gosh, what happens? We had absolute value of x plus 2. I have no idea what that is. If you just know what happens as these functions are transformed with these simple transformations of constant values, I feel like it gives you so much power mathematically of just being able to pop up with that graph without having to put it into your calculator or having to put out a table of values to graph it. There's just a lot that you can do right off the bat. And this skill is going to really come in handy as you work through your next couple of math classes. Are there any questions here on G? All right, so H, I already alluded to the fact that H was going to be a shift to the right, but we can show that in our calculators by entering, again, the absolute value, hit your math button, scroll to the right, enter your absolute value function, and this time we have x minus 5. Make sure the minus is in the bars. And the absolute value of x minus 5 is going to take that graph and shift it to the right 5 units. And that's what we're going to do. So the goal here is not to sit here and graph functions by plotting points. The goal is to use a base function that we already know something about and shift it around. So we're going to move our vertex over here to 5, and then we're going to create our absolute value graph. And you should see this behavior where your lines are parallel on the left and the right. So our graph h of x is f of x shifted right 5 units. And that means that in general, for any function f of x minus k is going to be a shift k units to the right. And then for f of x plus k, where the addition is happening inside the parentheses, this will be a shift k units left. And that you will just have to remember. Your exams in this class will be open notes anyway, so as long as you're taking good notes, you'll have all these. I really can't give you an online class and say your exam is going to be closed notes. It doesn't really make a lot of sense. So I hope you're taking really good notes. All right, those were the first two transformations. So we had a situation where we added and subtracted outside of the function and inside of the function, and we saw how those were different. So someone might be thinking, well, what if we had the absolute value of x and then the +2 was outside the bars? Well, that would just be a shift up 2 units. And then if you had a situation where you had x plus 4, the quantity was squared, well, then your graph would be shifted left 4 units. And we'll see some more examples of using those horizontal shifts inside the parentheses. Questions so far? I know, even though this is a really important lesson, I do feel like it's kind of a dry lesson. Not super exciting. All right, below is the graph of some function f of x. Graph a new function, f of x minus 2 plus 3. How is this new graph related to the original? You guys see if you can figure that out while I finish up my attendance. You got a shift that's happening up or down and a shift that's happening left or right. What will that do to your graph? Okay. We have a shift up 3 units. I think that one is the most obvious one. And then we're going to the right 2 units. Now, on your exam, I'm going to be asking you questions more similar to this, mostly because I want you to be able to take some generic function that I've given you and really read what's happening with the transformations and transform the function using that. So I'm going to ask you, tell me what the transformations are. That means you're going to tell me that we're shifting right 2 units and up 3 units, and then you're going to graph the new function. To do that, you're going to take each point and you're going to move it right 2 and up 3. So if I want to take this first point at -3, -1 and shift it, I'm going to take it right 2 and up 3. And that's going to be this same point on the graph. Maybe that's confusing if I put a dotted line, but essentially that's what we're doing here. We just moved this point up to here. We can do that with every point on the graph that that means anything to the shape of the graph. So this point right here, we're going to send this to the right 2 and then up 3. We'll attach these so you can start to see the shape of the graph transform as you move the graph around. And then this point up here at 1, 1, that's the final important point on the graph. We're going to go right 2 and up 3. 1, 2, 3. And there is your new graph. This is f of x minus 2 plus 3. Did you guys get that? I can't walk around the room and see what you did. Did anybody get this graph originally? Okay. The thumbs up works really nicely. Yes, wonderful. Good. Okay, wonderful. Wonderful, wonderful. Yeah, it's just harder to see and hear. Okay. Now, let's talk about some different types of transformations. The shifts left and right are the easiest ones. We're also going to have these transformations that occur when we use negatives in our function. Now, a square root function, you can graph this in your calculator. F of x is the square root of x. So to get the square root, you're going to hit the second key, and then you're going to hit the x squared key, and that will pop up with a radical. If you have a newer calculator, it'll give you a template. If you have an older one, it'll give you a radical and a parenthesis. And then you're just going to enter an x inside that template or inside your parenthesis. Now graph that, and you'll get what looks like the top half of a sideways parabola. That's because you're just, instead of taking values and squaring them, you're just taking their square roots. The values that are on the square root function are 0, 0, because the square root of 0 is 0. 1, 1, because the square root of 1 is 1. And then any values in between 1 and 4 you're not going to worry about, because you can't take the square root, for instance, of 3 and get an integer. But you can take the square root of 4, and the square root of 4 is 2. So you have a point at 4, 2. Don't worry about anything between 4 and 9. You're only worrying about perfect squares here because you have a square root function. The square root of 9 is 3. So when x is 9, the square root of 9 is 3. And to make the square root function, it starts at the point 0, 0. Remember, we can't take the square root of a value that's less than 0. So you're just going to start here at 0, 0, and then just kind of curve your graph upward and make sure you use an arrow to denote that this behavior continues as it moves upward and to the right. That is f of x. Now we're going to do two things to this function f of x. The first thing we're going to do is we're going to create g of x, and we're going to just make the function negative. Now, there's a big difference between these two. You're going to see what that difference is. But here, you're making the y value negative. You're just taking whatever the value is for the radical, and you're making it negative. For this one, you're putting the negative inside the radical. Very different scenario here. So for g, you're going to enter the negative square root of x. So make sure that your negative is outside of the radical, and don't use a minus sign. Make sure when you're doing a negative that you actually hit this negative button that's underneath the 3. If you use a minus sign, it's going to give you an error. So you have negative square root of x. And then we're going to graph it and see what happens. There's your original. The new one, interesting. The new one appears down here. Well, that makes sense because you basically took your function and made all of the y values negative. This function g is just f of x reflected over the x-axis. So in order to reflect this graph over the x-axis, all of the points that are above are now moving below. So you're just taking those points, popping them down underneath. So let's go ahead and graph G. These points will be repeated, but just reflected over the axis. So we had a point at 4, 2. The new function will have a point at 4, negative 2. 9, 3 will become 9, negative 3. And then just, keep this behavior for the function as it goes below the x-axis. And that will be g of x. Now, keep in mind, neither one of these is a full parabola. Each one of them just represents half of that parabolic shape. Questions about G? Okay. Now let's work on H. This time the negative sign will be inside the radical. So I'm going to take the square root of negative x. Now, some of you might be like, whoa, 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 how can we even do this at all? Because you're taking the square root of a negative number. Not necessarily. Remember that your variable x can always take on negative numbers if you want it to. What we're basically looking at here is a situation where x is going to have to always be negative all the time, because you're going to need to take a negative of a negative in order to actually be able to get a square root out of here. So go ahead and graph this. And now you're seeing a y-axis reflection. All of the same points that originally appeared in this graph f of x are now appearing on the left-hand side of the graph. That's because this function can only be defined for values of x that are negative. If x was positive, like x equals 1, then you'd be taking the square root of negative 1, which you can't graph. So let's go ahead and write down here that h of x is f of x reflected over the y-axis. Now, the functions that we're using here, the square root of x, the absolute value of x, x squared, these are all standard types of functions that we should become really familiar with graphing. So if you're wondering, like, how come we're only doing the square root of x with this type of example? I'm just showing you that with a particular type of function. But you're going to see this type of function with all different kinds of transformations, just these basic functions from the library of functions. So if we're going to reflect this over the y-axis, I'm going to put a point at negative 1, 1, and at negative 4, 2, and at negative 9, 3. And then we'll just graph it. Sorry, it should not look like it's going downward. Pencil kind of ran off there. And there's your function h of x. So in general, for any function f of x, the graph negative f of x will be an x-axis reflection. And f of negative x will be a y-axis reflection. Does anyone have a question on this example? you guys do 5. Take your function and graph negative f of x. Think about what type of reflection that is and recreate the graph. Okay, so we stated up here that negative f of x is an x-axis reflection. So we're going to take all of the points for this graph and we're going to reflect them over the x-axis. So let's see. Gian says that we should have, look at my points here. -3, +1. I agree. When we have -3, -1, we reflect this over the x-axis and it becomes -3, +1. -1, +1. Yep, I agree. This point is going to be reflected over the x-axis. It's going to move up. And then the last one is 1, -1. Yep, this point, when it gets reflected, it's going to go downward. Now, don't put any arrows on this graph. Thank you, Gian, because you don't want to include something that's not really being included in the original. So here's your negative f of x. It is just a reflection over the x-axis of the original graph. So this is just sort of the stuff that you're going to be expected to do in your homework. If it's a generic function like this, these are the ones that I'm going to assign for you to do on my math lab. I am going to assign you some of these to do by hand that have to do with your library of functions like x squared, the square root of x, the absolute value of x, just because I really want you to be able to work with those. But something like this where it's just a generic function that you can do on my math lab with multiple choice, I'm okay with that. Let's see. All right, the last type of transformation that we're working with has to do with what happens when we take our function and we multiply it by a number, or if we multiply inside the function by a number, and how big the number is. So let's start out by taking f of x equals x cubed. X to the 3rd power. When you graph that, you'll get this Elvis looking graph. I don't know, I was always told it was the Elvis graph, and I can't even give you a demonstration of why. This is the cubic function. It takes every point you pop in and it cubes it. Now, that means if x is 0, 0 cubed is 0. If x is 1, well, 1 times 1 times 1 is 1. If x is 2, 2 cubed is 2 times 2 times 2, which is 8. Now, we don't really go beyond that because 3 cubed is 27, and that's a really high number to have on our grid. However, for the cubic function, we can generate negative values. -1 times -1 times -1 is still negative. -2 times -2 times -2, also still negative. So for you have a point at -1, -1, and -2, -8. And when you combine these, you're going to get this, I kind of graph it in 2 pieces, whatever you find easiest. It should look pretty smooth as you can make it look. It's got arrows on both ends, and it's just kind of got this little jog in the middle. That's your cubic function. Now we're going to use it again over here. So you might want to graph it one more time because we're going to do 2 different things to it. So you've got the points here at 1, 1, and 1, -1, -1. And then you've got 2, 8, and -2, -8. These this is what I'm talking about. You should get used to these functions: x cubed, x squared, square root of x, absolute value of x. Get used to them. Know what points are on them so that you can reproduce them very quickly. Now, I actually think we should look at 2x cubed and 2x cubed before we start talking about what happens with 1/4. So let's do that. So the first one will be 2x cubed. And if this one, you have a little bit more of an intuitive sense for what's going to happen, I think. It's kind of hard to see it graphically. I mean, you can see it there, but it's not as obvious what's happening. What's happening here is that for g of x, every single value for f is getting multiplied by 2. So instead of just saying, all right, x is cubed, x is 1, that f of x is 1, that's fine, but now it's also getting multiplied by 2. So if x is 1, cube it and you still get 1, but then you multiply it by 2, and then you end up stretching this graph by a factor of 2. Let me get a different color here. So instead of having a point at 1, 1, you're going to have a point at 1, 2, and 1, negative 2. A little bit harder to see that with the particular shape of this graph. If x is 2, well, 2 cubed is 8, but times 2 gets you all the way up to 16. So that's a much higher point on your graph. If you would like, you can go to your table of values. Try to find something that, well, actually, it's only going to give you integer values. We can just show this being stretched by a factor of 2 by just kind of making your jog in the middle stretched out. If you'd like, you can kind of simulate where 16 would be. It would have to be somewhere up there, just to get a good idea of what's occurring with the stretch of the graph. So this would be g of x. And actually, I changed my mind. Let's do h of x here first. And if we're, why don't we answer this question actually right now? G of x is a stretch vertically by 2. Now, you can probably guess what's going to happen when we graph h of x. When you graph 1/4, if you find it easier to just use 0.25, that's fine. Or you can use 1/4, up to you. So 1/4 x cubed, graph that. Now you're looking at a much wider cubic function. What this is doing is it's taking every point that you originally had in your graph of f and it's making it 1/4 as tall. That means instead of having a point at 1, 1, you've got a point at 1, 1/4. So you're only going up to about right there. If you originally had a point at 8, 2, well, now you're going to have a point at 8, 1/2. I'm sorry, I said that backwards. If you had a point at 2, 8, then you're going to have a point at 2, and then take a quarter of 8, and you'll get to 2. I had those points backwards. And if you're not sure ever, feel free to go to your table and look at what's happening under y sub 3. When x is 0, you have 0. When x is 1, you have a quarter. And when x is 2, you have 2. So that we have this point at 2, 2. Do the same thing on the left. You have a point at -1, negative a quarter, and -2, -2. And you'll end up getting this still a cubic function, but it's not increasing quite as rapidly. It's flattened out a little bit more. So we would say that this function h of x is a shrink vertically by 1/4. Now let's compare that to what happens when the 2 and the 1/4 are inside the parentheses. In order to do that, I'm going to get rid of y sub 2 and y sub 3. And in the parentheses this time, instead of just writing 2x cubed, I'm going to use parentheses and say 2x quantity cubed. So 2x goes inside the parentheses, and then I'm going to cube it. So you'll have your original function being graphed first, and then the transformation is, again, this much thinner graph that goes up in a more narrow manner. And it's different than what's happening with g. The difference is that you're taking the value of x, you're multiplying it by 2, and then you're cubing it. Now, for some cases, you're still going to get the same point. But think about what happens when x is 1. Instead of taking 1 and cubing it, you're taking 2 and cubing it to get 8. So you actually get this value at 1/8. And another value at -1, -8. And, you know, those 3 points are enough to connect your graph. If you can't hardly get that jog in the middle, that's okay. Do the best you can. And then, last but not least, when we take this 1/4 and we put it in the parentheses, I'll have parentheses 0.25x, close your parentheses, cube it. Now graph that. Now you get a much wider cubic function in this case, because you're taking your value of x, you're multiplying it by 1/4, and then you're cubing it. So whereas normally we would have on this graph 1 cubed is 1. Well, now we have 1/4 cubed, which is 1/64, which is an extremely small value. You can't even hardly put it on your graph. It's so close to the x-axis. And then when you take x equals 2, well, 2 times 1/4 is 2/4, which is 1/2. 1/2 cubed is 1/8. So again, so small that it's hard to even graph. When x is 3, you'll take 3/4 and you'll cube it, which is 27/64, which is still not even a half. And you can also get these values from your calculator table if you want to do that. It's not until x is 4 that you even get here to 1. When x is 4, 1/4 times 4 is 1, cube it, and you still get 1. And that's when you start to get these values to change a little bit more. When x is 5, you get 125/16. If you look at this in your calculator table, it's 1.9531. It's almost 2. And when x is 6, you get 3.375, which is almost 4. And then these values start to get, actually it's not 3.375. I put it up a little bit too high. But you can see these values changing a little bit more rapidly as you move away from 0. So this would be your function m of x. So let's summarize real quick here for k and m. So k is a horizontal shrink. And m is going to be a horizontal stretch. Okay, here's what my plan is, because I'm over time now. I am going to, on my notes, oh, sorry, I did not realize how far up there I was. I'm going to summarize these for you. You already pretty much have them written down, but I'm just going to make a little bit of a summary of what we talked about. And then next time, we'll just go through these examples using our information. So I just want you guys to do some homework problems that are based off of just using the original transformations we talked about, and we're going to start combining them all next week. And we'll finish up 2.5. 2.7 is really short, and then we'll do 2.6, and then we should be all set for our exam a week from Monday. I do plan on giving a super short quiz Monday just because I want to, first of all, make sure you guys are used to doing them and get you some sort of feedback right away since we do have that exam coming up. I will be on for another about 10 minutes. Feel free to stick around. I have some homework posted for you. If you hold on a minute, I'll shave a little bit of it off there and I'll put it on next week's. Once you start on it, I don't think I can take anything off. But I'll see you Monday. I'll send you an email giving you directions for your quiz. Stick around if you have questions. Have a good weekend.
The quiz and test, they're open note, right?
Yes, open note.
Okay.
Yeah.